All right, there we go. Okay, so what I want to talk about today, I want to take a look at, let's put all phones and everything completely away. Got it. This might be our last day here, you never know, for this till next year.
You mean in life?
You never know that.
Are you grateful for today?
For today. Maybe tomorrow, maybe the next day. It's supposed to really start snowing, so you never know. Okay, so I want to get through some stuff. I want to show you something really cool. This is interesting stuff. We're going to talk about a new kind of a locus today. So I want to refer you back to the discussion we had a little bit ago. We talked about circles, and we said that a circle is the locus of points that are equidistant from a common point that we call the center, right? And that's a pretty easy one to think about. That makes a circle. We're going to think about a different locus of points today. So here's how we want to define this. We're going to have, I'm going to set up on the plane here, we're going to have a line, which we're going to call the directrix, and we're going to have a point, which we're going to call the focus. And we want to pick the set of all possible points, the locus of points on this plane that are the same distance from the focus and from the line that we call the directrix. Now, before we do this, I want you to remind me real quick, if we have a line and a point, what's the shortest way to get from the point to the line?
Line.
Okay, well, straight, but how is the path going to be related to the purple line? Perpendicular, good. So when we talk about the distance between a point and a line, we're always implying that we're talking about the perpendicular distance, right? So this would be, that's the distance D, and that's got to be a right angle, okay? All right, so here it is then. Now notice, I built this Geometer Sketchpad document to demonstrate this. It's pretty cool. It measures the distance from the focus A to this random point C that's going to be one of our locus, part of our locus of points, and also the point from B to C, right? Notice that they're the same, and they're going to stay the same. It also just tells us that this angle right here is 90 degrees. So we're actually measuring the perpendicular, the shortest distance, right, Manuel? Let's get that away, please. Okay, so look what this looks like. As I drag this thing down there, look what happens to the location of that point. It kind of changes. It follows a distinct path, right? But notice that the distances, as they change, are always staying the same, right? Okay, that's what it's going to look like. It does not make a circle this time. It does something different, right? What do you think it's making?
Triangle. A longest.
Let's see. Let's see what it makes. I'll construct the locus of points.
Parabola.
It's a parabola.
It says parabola in the corner.
Oh, it does. There you go. There's the first hint. Okay, so it is a parabola. Yeah. So this point follows along the path on that parabola. Okay. That's the parabola is the locus of points equidistant from a line and a point. Okay. All right. So what we want to do. And I want you to notice something here. If we look at this parabola, you've dealt with parabolas before, right? Parabolas, you dealt with that in Algebra 1. Parabolas have, well, what kind of symmetry? Just looking at that parabola, what kind of symmetry does it have? What kind? It is, it's bilateral.
Is it
Okay.
symmetrical? Asymmetrical.
No, it's symmetrical. It's symmetrical. It's got bilateral symmetry. That's kind of our biology term for it. In math, we call that just maybe line symmetry, right? So it's got line symmetry about a line that goes straight down, perpendicular to the directrix, right? So this can be our line. Okay, everybody agree?
Yeah.
And okay, so there's the line of symmetry. What do we call the intersection of the line of symmetry and the parabola? That's a special point. Remember what we call that? This point right here?
Isn't that the
intersection?
That's the vertex.
Vertex.
Yeah. That's the vertex, right? So the vertex is sort of, quote unquote, that's the point of the parabola, right? So if I want to identify this parabola, one thing I'm going to need to know is where the vertex is, correct?
Yes.
Okay? So that's I can slide this parabola around in the plane. The other thing I'm going to need to know is maybe, is the parabola a tall and skinny one, or does it get widened out?
Widened.
Well, but we could change that, right? We could change that. We could, by dragging this thing down, look what it does. It changes the parabola. It's going to make the parabola skinnier if this distance between the focus and the vertex gets small. That changes the shape, right? It makes it a skinnier parabola. If the distance between the focus and the vertex is large, it makes it a wider parabola, right? So really, the only parameters we need are just the location of the vertex, and we need to know how big this distance is. Well, we're going to call that distance P, turns out. Okay, so that's the other parameter that tells us the shape of the parabola. Okay, we want to come up with an equation for this. All right, so here's what we're going to do. This is, if you have any interest in math, possibly, looking at math in the future, engineering, even if you're not, this is pretty interesting. We want to take this simple concept and we're going to use this to come up with an equation that's going to represent all parabolas in terms of those parameters we talked about, the location of the vertex and the length of the segment connecting the focus to the vertex, right? So here's our parabola. If I drew it on here, it's just there's the focus and there's the directrix. So it's going to be this set of points that are equidistant from both. So kind of like that, basically, right? There's our parabola. Now notice that the way we've got this, the symbols that we use here in geometry, that means congruent segments, doesn't it? I put those dashes in there. So this is telling us that the distance between the focus and some random point in our locus, a random point that's on the parabola, has to be the same as the distance from that random point to the directrix, right? To make things really convenient here, let's start off by putting our vertex at the origin, right? So this is the x-axis, and this is the y-axis, and the vertex is right there at the origin, at the point 0, 0, right? Okay, so then what are we going to call the focus? Well, we said that we called that distance between the vertex and the focus, we called that distance P, and so the coordinates of the focus then would just be the same x-coordinate, but now we're going to move up by a distance P, so the y-coordinate becomes P, agreed? Okay, so we get 0P. What's going to be the coordinate of the line on the other side of the vertex, the point that sits on the directrix, right, sort of below the vertex? Well, isn't that going to be same x-coordinate, but this time we're going to go down by P instead of going up by P. And so it's the point 0, negative P, right? The directrix is a line that goes forever in both directions. What's its equation going to be? What's the equation of a horizontal line?
0.
It's going to be what now? How do we say that? A line that goes through the y-axis? Y equals, well, whatever the y value is of every point. Let's just look at the y-intercept. So y equals negative P, right? Okay, so then all we've got to do is just set up an equation that says that distance is equal to that distance. Okay, let's do that. So let's go ahead and let's make this distance, to color code this, let's make this distance green. How about it? Right, and let's just, all we're going to use is the distance formula. Right, the distance, I'll write it up here. The distance formula is just the square root of x2 minus x1 squared plus y2 minus y1 squared, right? And for this green segment, we're going to say that this point is x1, y1, and this purple point up here has coordinates x2, y2, right? And we'll just plug those in. So the square root of x2 minus x1 is just the square root of x minus 0 squared, right? The square root of y minus p, or excuse me, y minus p squared just looks like the quantity y minus p squared, right? So this is our distance formula when we use the green and purple endpoints, right? Make sense?
Yes.
Okay. about the other side? Well, on the other side, let's make this one orange. How about? We're going to look at this distance, and it has to be the same. They have to be the same, equidistant, right? So this one, we can either use the distance formula, or we could even take a shortcut on this one. Notice that the x-coordinates are the same for both of these points, for the purple point and for this orange point down there, right? So if the x-coordinates are the same, the distance is really just the change in y, because the x's don't change at all, right? And we can see that in the distance formula, but we don't even need to bother with it. We could just say that the length of this one is going to be this y value minus that y value. Well, what's y minus negative p? If I subtract a negative, what am I doing?
Positive.
It's just y plus p. So this whole thing could really just be replaced by, if we want to, by y plus p, right? Okay. Well, if we simplify a little bit, x minus 0 is just x, right? So that whole first term would just be x squared. Otherwise, it stays the same. On this side, we don't need to change anything. We can just leave this as y plus p if we want it. But now we want to get rid of the radical on this side. So what would I do to both sides to undo the radical? How do you square it? I could square it, right? Because to undo a square root, I would square both sides. So if I square both sides, that goes away, and that side gets squared, right? And so I end up with x squared plus the quantity y minus p squared equals the quantity y plus p squared. That's pretty good. Looks better all the time, right? What if we were to expand this out? So if I took y minus p squared and I multiplied it out, y minus p times y minus p. If I do that, here's what's going to happen. This stuff right here becomes that if I multiply it out. Well, we could do that, but we'll just save time. Okay? What about on the other side? If I multiply out y plus p squared, it's just going to turn into that stuff. Okay, make sense? And so now why do we do that? Well, look, there's some common terms on each side, the y squareds and the p squared. If I subtract y squared from both sides, those are going to go away. If I subtract p squared from both sides, those go away. And all we're left with is this, even better. Now notice that these are like terms. They're both numbers of py, right? So if I have negative 2py on this side and 2py on this side, I could just add 2py to both sides, right? And that's going to get rid of this and make this a 4. So my final answer just looks like x squared equals 4py. That's pretty remarkable, right? We got a simple equation from that. All we started off with here, we started off with just a general parabola with a vertex at the origin. And we didn't specify the value of p, did we? Right? And so we found out that if we do that, the equation of the parabola is x squared equals 4py. The only unknown that time is just p, right? That's pretty good, but it'd be better if we were a little more general. The one thing that we did up here that wasn't very general is we limited ourselves by choosing the vertex to be at the origin, right? So the formula that we developed is only going to work for parabolas with a vertex at the origin. We don't want that. We want this to work for any parabola with a vertex any place, right? So all we really have to do is then take our result and just translate the vertex to the coordinates hk, where h and k could be anything, right? So let's slide it horizontally by h and vertically by k, and that's a really simple step for us. All we've got to do to accomplish that is this, right? If we translate the vertex to hk, all that means is we're going to replace the x with an x minus h, just like we did before, right? How did we translate a function horizontally, right? We just included this number h subtracted from x that tells us the horizontal translation, right? Now in the past, we always wrote out our functions as y equals, and so k got kind of stuck on the right side just as a constant. But if we were to include that with the y, we would do the same thing here on this side. If we want to translate something vertically, well, we're just going to subtract k from y. It works the very same way. And that's going to translate something up or down. And so we end up then with this completely general equation for a parabola, right? Look, this is written in terms of what parameters. What are the numbers that we could choose to create a very specific parabola? What numbers could we plug in here to create our own individual parabola? Gage, what's one? What could we do here? I mean, what values could we plug in? For what though?
H.
Okay, for h, yeah, we could pick the x-coordinate of the vertex.
Yes.
We could plug in some number for k, right? And then we're choosing where the vertex of that parabola is going to be. It's our choice, right? We get to choose. What's the other thing we could choose? P. If we pick a value for p, we're going to choose what's the shape of this parabola. Is it tall and skinny, or is it short and wide, right? See what I'm saying? Okay, so there you go. The one last thing we can do is the one that we drew was a vertical parabola, one that opened up vertically, right? We could take the same thing, same idea of a parabola, and we could instead make it horizontal by just taking the inverse. Now think what an inverse does. An inverse just switches x and y, right? And it'd have to switch h and k also, and I'll show you in a picture here. But it's going to have a certain symmetry that's going to make this parabola go from being vertical to horizontal. So let's just say we've got some random parabola out here with coordinates of the vertex that are hk, like that, right? When we take an inverse, we're just switching x and y, and so instead of going backwards h and up k, I would go down k, I'd go over k and down h, right? I'm just going to flip those two. Does that make sense? So we're going to end up with new coordinates kh, we just flipped them, right? And what's the parabola going to do now? When we graph inverses, they have symmetry about what line? Do you remember? Oh, okay, good. It's this line, isn't it? It's the line y equals x. So we're going to take this blue parabola and we're going to flip it over that line, and it's going to become this one, isn't it? I didn't draw it very well, but you get the idea, right? So that turns it sideways, right? So now we got a sideways parabola. So what do we end up doing then? The x minus h became a y minus k because we swapped the x for a y and the h for a k, right? The y minus k turned into an x minus h. So that's all you got to do. If I want to take this vertical equation of a vertical parabola and make it a horizontal one, I'm just going to flip those positions of those things, right? That's it. Okay? All right, last thing I want to just point out to you, and then we're good to go. We can try one of these. This parabola, okay, about p. So listen to this very closely, because this is a point that people oftentimes get confused about. So if this is the vertex, and that's my parabola, first of all, notice that parabolas are always going to open towards the focus, right? So the parabola is always going to swallow the focus, right? P is defined as being the distance starting at the vertex and going to the focus. So think of it as an arrow. That arrow is pointing in the positive direction. It's actually, think of it like a vector, right? So which is an arrow. So that's positive value of P. That means that the parabola opens up. Now what if we had a directrix and a vertex here and a focus there? So now P would start at the vertex and it would point in the negative direction. So the value of P would be negative this time, right? Because it's pointing down. What's that going to make this parabola look like?
Upside down.
It's going to be upside down. Because it has to open towards the towards the focus, right? See what I'm saying? So negative values of P are going to cause a vertical parabola to open down. Positive values of P cause a vertical parabola to open up. Positive values of P are going to cause a horizontal parabola to open to the right, which is the positive x direction. A negative value of P is going to cause a horizontal parabola to open where? What do you think? To the left. Yeah. Okay. So try that. Think about this for a second. We want to write the simplified standard form equation of the parabola with a focus at the point -1, 0 and a directrix at x equals 1. So maybe we want to just sketch a little picture here to kind of orient ourselves. In the future we won't maybe need to, but for now let's do that. Okay, so we said that the focus goes at -1, 0, right? So that's F. And the directrix is a line x equals 1. Is that going to be a horizontal or a vertical line? It's going to be vertical, isn't it? Good, so it's going to go through the point. It's going to go through this point right here that has coordinates 1, 0. Right? So there's my directrix. So all I need to know, this is going to be which one of these two equations is going to apply to this one. It's going to be this guy, isn't it? Right? The way I always remember this, if you think back to Algebra 1, here's how you can remember which equation goes with vertical parabola and which goes with horizontal. If you think back to Algebra 1, the parabola that you dealt with the most was just the plain vanilla one, y equals x squared, right? That's just a regular old parabola that opens up. But notice which variable is being squared. X is being squared, right? So a vertical parabola is going to be this guy because the x is being squared, right? So for us, this is going to be a horizontal parabola, isn't it? It's going to have to open up sideways because the directrix is vertical, right? And so the one we're going to want to use is this guy. That's the one that fits us, right? So all we've got to do is just plug in the values for k, p, and h, and we got it. So let's find the vertex. Where's the vertex going to be? It's got to be halfway in between the directrix and the focus, doesn't it? So that's going to be that point right there, isn't it? Right? Okay. Now, it's going to be horizontally aligned because this is a horizontal parabola. The vertex and the focus are going to be horizontally aligned, so they're going to share what coordinate then? What coordinate's going to stay the same? The y coordinate is, isn't it? So we know for the vertex right away, we know that the y coordinate is 0, and the x coordinate is just going to be what we get when we go halfway in between -1 and 1. Well, what's that? 0. So the vertex is at the point 0, 0. Okay? So that's telling us the values of h and k, isn't it? So all we got to do is plug in a value of 0 for k and 0 for h, right? If we were to draw our parabola, it would just look like that, right? Now what about p? That's the last thing to do. P is the direction and distance that an ant would crawl in a straight line to get from the vertex to the focus, right? So that's an arrow that starts here and points in which direction? Left. So it's going to go left how far? 1. And it's going in the negative direction, so what's the value of p going to be? -1. That's it. Okay? That's all we got to do. Plug those in and we're done. So what do we get? Y minus 0 is what? Y, right? So I end up with y squared equals, what's 4 times -1?
-4.
And x minus 0? That's it. Okay? That's it. All right, let's try one that's a little harder. Try one like that. How about it? Is the directrix going to be horizontal or vertical?
Vertical.
It's going to be vertical, isn't it? Right? So maybe we don't even have to draw the whole xy plane. Maybe we can just kind of draw the directrix and the focus and go from there. All right, so our directrix looks like that. That's the line x equals -5. The point -7, 1, is that going to be to the left of or the right of the directrix?
Left.
left, because -7 is further left than -5, isn't it? Right? So the focus is going to be out here somewhere with coordinates -7, 1. All right, so then where does the vertex go? So it's going to go, has to go in between, right? It's going to go in between. Now, what coordinate do you already know? It's going to be, yeah, what's the y coordinate of this one going to be for sure? No. It's got to be 1, doesn't it? Because this one is 1, and they're lined up horizontally. Everybody agree? Yes. Okay, so the vertex is going to have y coordinate 1. What's the x coordinate going to be? If it's got to go from -7, it's between -7 and -5, what's it going to be? -6, right? So based on the fact that that's -5 and that's -7, it's going to be -6, right? So there's h and there's k, right? What's the value of p this time? Because I start at the vertex and I've got to go in the negative direction. How far? 1, from -6 to -7, right? So there's everything I need, right? We're going to take the equation of a horizontal parabola and just plug in -6 for h, 1 for k, and -1 for p. And that's it, right? And what do we get? Y minus 1 squared equals 4 times -1 is -4 times x minus -6. Makes it x plus 6. Done. That's it. Okay, get the idea? Try one of those. If you get that, I feel like we got it. That's a lot to cover. We have to call our quits if you can get this. Yes, you may. Okay, so let's try one more of those. Oops. Okay, try that one. Try that. See if you can come up with the values of h and k and p and plug it in. No, Ashley? Where does the point, the focus at point 0, 4 go? Left or right of the director?
Right.
Right?
It's on the line.
It's going to be left, isn't it? That's an x value of 2, and that's an x value of 0. So it's going to go over here, isn't it? So we got the point 0, 4 for our focus. And so then think of, I know that the axis of symmetry of the parabola is going to be horizontal. It's going to open sideways, isn't it? So let's just draw, whoops. So this is going to be like the axis of symmetry of the parabola, right? If we want to add that. What are the coordinates at this point going to be right here while we're at it? It's going to be 0, oh, what's 0, no, it's going to be 2 what?
0.
No. 2, 1. If it's horizontally aligned with this one, 4. Yeah, the y values have to be the same, don't they?
Yeah.
They're both equally high, right? So then the vertex has to go in the middle, doesn't it? So it's going to be right there. That's V. And what are its coordinates going to be? The y coordinate is what? 4. What's the x coordinate going to be? If it's halfway between 0 and 2, 1. Okay? What's the value of p? Let me think. Value of p. So, Brendan, where does p start? It's the vector that starts where and points where? Starts in the center. Good. So starts at the vertex and points at which point? Points to which one?
X.
Points to f. Yeah. So that's the vector that represents p. So what's its value then? Pause. Okay, so the value is just how long it is, right? So how long is that vector? If it's starting at x equals 1 and it's moving to x equals 0, it's 1, and what's the sign?
Negative.
Negative, because it's pointing in the negative direction. Good. So now we got everything. We got p, and we got h and k, because those are the coordinates of the vertex, right? So then what's this? See if you can remember. What's going to be the equation of a horizontal parabola, the standard form equation of a horizontal parabola? So why don't you get rid of that? What's it going to be?
Y minus k squared.
Good. Y minus k squared equals 4p times. Good. Just x minus h. That's the only one that's being squared. So then we're going to plug in, for h, we're plugging in what? 1. For k, we're plugging in. For p, we're plugging in.
1. Negative 1.
Yeah, so that's it. Just what do we get? Y minus 4 squared equals 4 times negative 1 is negative 4x minus 1. That's it. Questions? Does that make sense? Okay. Real quick, I'll tell you why parabolas are so important. So why do we deal with these parabolas? They have a really important, they're very valuable to us in physics and in engineering. So here's what they do. Parabolas have a unique quality when, like let's say, why is it, do you suppose, where's there a parabola in your house maybe?
The doors.
Your pipe, like water.
What about when you're in the Atlantic Ocean?
Well, it might be mounted on your roof.
Oh, the chimney dish.
Oh, satellite dish. Okay.
Oh,
A satellite dish
chimney.
is an example of a parabola. Here's why it has that shape. Pay attention. This is interesting. So the reason it has that shape is because when light or any kind of a signal that can be reflected comes into a parabola, if it comes in from a long ways away, so it's parallel, and think about think where that signal is coming from with your satellite dish, right? It's coming from, I mean, really it's going to be tens of thousands of miles away, the satellites are. So the satellite is beaming out information that's going to be that's going to be captured and decoded by your TV, right? But first you got to get the signal. Well, the further you are away from something, the more, oh darn it, the more parallel the rays become. So if we look at this, for example, if I've got a small circle, because like when if I were just to shine flash a flash bulb, the light is going to spread out spherically, isn't it? Right? As it spreads out, it attenuates. It gets weaker and weaker because it gets more spread out in space. Everybody agree?
Yes.
And so if I were to look at this, if it's a very small circle, look what's happening to the light rays that start at its center. If we're going to try to capture some of these on like a photographic piece of film or something, they're going to be spreading out at a pretty pronounced angle, right? To get from the top to the bottom. But if I make this circle much, much bigger, if I make this circle much, much bigger, now the center of the circle out to that same little paper out here, those rays don't go through a very big angle anymore, do they? Right? This is only a meter, but imagine if I made that millions of meters, right? Then you can see that those rays, that this curvature would just about go away, right? The spherical wavefronts that are getting to your satellite dish from the satellite are coming in just about flat. There's almost no curvature because the circle is so, the sphere is so big, right? And so the rays are coming in essentially parallel. When rays come in parallel into a parabolic reflector, here's what happens. The rays all get reflected through the focus, which we call the focal point of the parabola. Like that. Every single ray that comes in gets reflected through that one point. Why is that valuable?
So everyone needs it.
That's where the dongle is. That's where the antenna is on the satellite dish, right? You notice that satellite dishes, first of all, satellite dishes, they're just going to be a small part of this parabola, right? It's too expensive to build a bigger one. Just a small part of this, but then there's always going to be some little feature here, right, where there's going to be some mechanism that holds the antenna up there, and everything gets bounced to that one central location, right? So what's that do? Then it takes the signals coming into a fairly large area, and it reflects them all back onto one single small point, which amplifies the signal, right? Now you can reverse that too. If you think about like what your cell phone does, if you make a call to New York, for example, you ever think about that? Your cell phone only communicates for a few miles. I mean, it's really a weak antenna in your cell phone. So in order for your cell phone to work, you have to be in fairly close proximity to a cell tower, line of sight to a cell tower. So the cell tower communicates with your cell phone, it picks up the signal, amplifies it, and then what's it do? Well, one of two things. It either sends that signal off to a bigger cell tower somewhere, or, notice this, whenever you're driving through really remote areas and the cell towers are kind of far apart, you'll always notice on those cell towers that they typically have a radar dish, parabolic dish, pointing at the satellites, right? Because they're so far away that it's not cost effective for them to be sending this signal out to some central place that's going to beam it all up. They just have a little radar dish right there, and they send the signal that's been amplified from your cell phone up to a satellite. The satellite redirects it to the East Coast. It goes to New York, and it comes down into another cell tower, which sends it out to your buddy who you're talking on the cell phone with in New York, right? That's how it all works. Well, how do they get that signal from that cell tower up to the satellite, right? They can't just beam it out in all directions because it would get too weak. They've got to be able to send a focused, what we call in physics a collimated beam, out towards the antenna on the satellite, right? And so what they do is they just do the same process in reverse. When they want to send that signal up to the satellite, where do they point it? They don't point it up, they point it down at the dish, right? So the signal is sent out like this towards the satellite dish, and what do you suppose it does when it bounces off the satellite dish? It starts at the focus. It comes out parallel. Right? And so then you get all these parallel, it doesn't spread out, it just stays in the same parallel pattern. You got this focused beam that goes all the way up to the satellite and communicates with the satellite. Right? So these things are huge. I mean, they play an enormous role in math and physics and engineering. Right? All right. Good enough.